Hello and welcome to the session number 4 of the Theory and Applications of Network Coding class. In this session we'll focus on the index coding problem. So the index coding problem relies on the notion of side information available at intermediate network nodes. The side information refers to packets known to this node but not really required to this node. So how side information can be obtained? There are several reasons for this side information to be stored at nodes. One of them can be due to the broadcast nature of wireless spectrum. So consider, for example, a multi-hop wireless network, ad hoc wireless networks in which packets send nodes to other packets through multi-hop connections and through intermediate nodes. So, for example, in this network, suppose client number 1 wants to send packet P1 to node 3. So in order to do this, it sends it first to its neighbor, node number 2, and node number 2 will then forward this packet to its destination, node number 3. So due to the broadcast nature of the wireless spectrum, whenever node number 1 sends packet P1 to node number 2, not only node number 2 can decode this packet, obtain this packet, but also node number 4 will be able to obtain these packets as well. And this again due to the broadcast nature. Once we're sending nodes to neighboring nodes, we actually broadcast these packets, which allows other nodes in vicinity of the sender to obtain this packet. So once client 1 sends packet P1, nodes 4 and 2 will also receive this packet. Similarly, when node number 2 sends packet P1, nodes 5 will also get it because it's located close to the node number 2. So as a result, when we have packet transmitted from node 1 to node 3, all other packets in the network will also have a copy of this packet, and they can utilize this as a side information. So let us see how the side information can be used. So consider the following setting. Suppose we have an access point that has 4 packets from P1 to P4. Each of those packets needs to be forwarded to one of the clients. For example, in this picture, packet number 1 needs to be forwarded to client number 1, packet P2 needs to be forwarded to nodes number 2, and so forth. P3 needs to be forwarded to P3, and P4 needs to be forwarded to client number 4. So now for each client we have 2 sets of packets. One of the set depicted on the upper part is a required packet, or set of the packets that client number 1 desires. And in the bottom we'll show the side information. So for example, client number 1 have access to packets P2 and P4, which is not really required by this client but can be used by this client as a side information. Similarly, node number 2 has clients P1 and P3 as a side information. Node number 3 has packets P2 and P4 as a side information. Node number 4 will have packets P1. How the side information be obtained? Again, this can be obtained due to broadcast nature of wireless spectrum. For example, suppose suppose this packet P2, for example, can obtain by this wireless access point by some other client. So suppose we have some other client here which sent P2 to this access point, but also clients that were in vicinity of this node were able to obtain this packet and stored it for some period of time. So the index coding problem seeks to minimize the number of transmissions that made by access point in order to satisfy the demand of all clients. For example, one of the solutions to index coding problem can be send uncoded packets. If we send uncoded packets, then in this case we need to make minimum 4 transmissions. So access point needs to transmit P1, P2, P3, and P4, and uncoded way. And of course, this is not efficient, and this is not utilizing any side information available at the client. So this is definitely not an optimal solution. So let us think about a better solution to this problem. And this could be perform combinations, perform coding. So to send, instead of sending original packets uncoded, we will set a coded combination of packets. So one of the possible solutions is to transmit two combinations, so just two instead of four. And the first combination will be P2 plus P3. Again, addition here will be performed over some field. So for example, here we can use a field GF2, and which will correspond just to bitwise exclusive OR between bits and packet P2 and P3. So as we see, the first transmission will satisfy client number 2, because client number 2 will be able to use the side information P3 to obtain packet P2. Again, it will receive P2 plus P3. And again, in this index coding problem, we assume that this broadcast channel is actually lossless. So client number 2 will receive P2 plus P3, will substitute P3 and get P2. If you're looking on client number 3, it will receive again P2 plus P3. It knows P2 because it's its side information, and then it will be able to substitute P2 and get P3. Similarly, packet number 2, which is P1 plus P4, can be used by client number 1 to decode P1. Client number 1 knows P4, so it can substitute and decode P1, and it can be used by client number 4 to decode P4. Again, client number 4 knows P1, so it can substitute P1 and obtain P4. So now with two transmissions, we can satisfy all clients in this network. Okay, so this is the index coding problem, and this is one of central problem in wireless network coding. And we will study this problem later on in the class and discuss different interesting properties of this problem. So this problem was actually defined before network coding was popular, so it's from 98, and actually it was done in context of broadcasting packets from a cellular network, which has a low capacity backend channel between clients, so different clients can have certain set of movies, and we need to broadcast new movies to clients, and clients of course can utilize side information available at those nodes to make this transfer more efficient. So we can send a combination of movies, and each client will be able to decode individual packets, individual movies that they want. So we'll see that this problem actually equivalent to many network coding problem. In particular, we will discuss reduction of a set of network coding problem. So reduction of a network coding problem to index coding, and from index coding to network coding. So all of those problems are closely related to each other. Also, there are a lot of works on this problem that shows interesting properties. For example, the nonlinear codes in this scenario will outperform linear codes, which is a little bit surprising when you look on this problem in the first place. Okay, so the last topic in this session, which deals with introduction, it's with the physical layer network coding. So physical layer network coding will take one step forward. So as we said, like traditionally in network coding, the packets are combined and the intermediate nodes on the network. So here with the physical layer network coding, the packets will be combined in the air or in the physical layer. So let's consider the settings that we already considered in some of the previous lectures. And here we have clients 1 and 2, and those clients want to exchange packets through a relay node. So for example, client number 1 wants to send packet A to client number 2, and client number 2 wants to send packet B to client number 1. As we said before, with traditional network coding, traditional way of forwarding, we need at least 4 transmission. In this case, client number 1 will send packet A to the access point, and access point will send packet A to client number 2, and the same with client B. So we need 4 transmissions in total. So if we want to measure the delay, so we'll require 4 different time slots to transmit this packet, to make this exchange happen. So with network coding, traditional network coding, not physical layer, network layer network coding, we'll need 3 transmissions, right? As we said before, clients 1 and 2 will send packets A and B respectively to the access point, and then access point can broadcast it. So we can reduce it from 4 to 3 by using general network coding principles. With physical layer network coding, we can do it even faster. And the idea is to just let clients 1 and 2 to broadcast, to transmit A and B in the same time slot. If you allow this, and of course it's very kind of superficial way of analyzing what we're doing right now, because to analyze it properly, we need to consider different modulation schemes involved here and physical layer protocols. However, we can see that when we transmit those 2 packets simultaneously, the relay will be able to decode some combination of those 2 packets. So it's not necessarily a combination over a finite field. It's more similar to addition over real numbers. However, the main principle is that relay doesn't really need to know individual packets A and B, because it's just helping. So if a relay receives the combination, for example, just sum of this packet A and B, and plus some noise, so then in the next stage it will try to get rid of this noise using some techniques of channel coding to decode, to denoise it, to get rid of this noise, and broadcast this combination again to those nodes 1 and 2. Then nodes 1 and 2 will be able to decode packets they need from the packet broadcasted by the relay node. So in this case, we will reduce the number of time slots required from 4 to just 2. And there is an entire area of physical layer network coding with a lot of papers published over the recent years. So this will conclude session number 4. Thank you.